Here's a typical problem. What's the pH of a 0.1 molar solution of sodium acetate? And the Ka of acetic acid is given, not the Ka of sodium acetate. So this is a problem that students have a little trouble with because they look here, they say sodium acetate, well, why does that even have a pH? So let's look at that idea first. If we look at some solutions, here we have a green solution, and that is water with a little bit of universal indicator in it. If we put in salt into the water, some salts don't change the pH at all. So here's a situation. Here's sodium chloride. Turns out sodium chloride does not change the pH. The pH of that would stay 7. If we put in some ammonium chloride, that actually makes the solution acidic. And the situation we're looking at right here is sodium acetate, and it turns out that that actually makes the solution basic. So first step here is to realize that if we have a sodium acetate solution, that's going to change the pH. Now, why would that do that? Here is an equation for acetic acid in water, and we can see that it is going to dissociate a little bit. We're going to get some H3O+, and we'll get the acetate ion. Now we could go back with that and say, okay, this is an acid, and because it's an acid, the H2O here must be a base, and in the reverse reaction we can see the H3O+ must be an acid, the conjugate acid of the H2O, and the acetate ion here, this is a conjugate base, the conjugate base of acetic acid. And that is the part that makes this very, very important, is that when the acetate ion gets into water, it can act as a base and make the solution basic. And we saw that because of the blue color before. So the reaction we really care about here is acetate ion. Now notice we don't put in the sodium because the sodium is just a spectator ion. It's going to drop out anyway, so we're concentrating on the acetate ion. The acetate ion plus water turns into acetic acid and leaves some hydroxides floating around. Now, if we want to solve this problem, then we need to go back and we're going to make an ice box. And remember, for our ice box, we'll make a column for each chemical. The water is a liquid, so we really don't care about it, so we'll get that out of the way. This first row here are our initial concentrations. The last row are equilibrium concentrations, and the middle row is a change that we go through to get from the initial to the final. We already have here that this is a 0.1 molar solution, and it's implied that this is 0 molar and that this is 0 molar because we didn't say we put any of that in. Now we can already see we're sort of running out of numbers. Another piece of this that we need, though, is we need to have a K for this reaction. And because we're talking about a solution that's going to increase the hydroxide concentration, then we're actually talking about a Kb. So the Kb for this reaction is going to be the concentration of acetic acid times the concentration of OH minus divided by the concentration of acetate. And to get a value for that, we have to go back to another set of equations. Here I've written the equation for acetic acid as it dissolves in water and dissociates. So we would call that the Ka. And we have another reaction, the second reaction we just wrote on the other screen, which was acetate in water turns into acetic acid and hydroxide, and we know that's the Kb. And what we can see is if we put these two equations together, then the acetic acid is going to cancel out, the acetate ion cancels out, and what we're left with is two waters turn into H3O+ and OH minus. And for that, we might recognize that that is the Kw. So when we're all done, we say, okay, if I took the Ka times the Kb, I could get the Kw, and what we want is I can say Kb is equal to Kw divided by the Ka. So that's why in the initial problem they gave us the Ka of acetic acid because we need that to make the Kb. This is going to be 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. That was given to us in the beginning. And we get all done. I think that is 5.6 times 10 to the negative 10. So we're going to need that number when we do our icebox. So back to the icebox. We can see that we now have a number for this, 5.6 times 10 to the negative 10. We have our initial concentrations, and now it's time to use some variables. So we are trying to get a pH. If we want a pH, we need to know the H plus concentration or the OH minus concentration. So let's say that this is X. Okay, X will be our concentration of hydroxide at equilibrium. Well, if we start with 0 molar and we end up with X, then we must have made X. And this middle row, the change row, remember that when we get any variable in here at all, we can do all the whole row because it's going to follow the coefficients of our balanced equation. So it's a 1-to-1 to 1-to-1 equation. So if we make X hydroxides, we must also be making X acetic acids, and we must be using up X acetates. So down here in our equilibrium we have 0.1 minus X, and this is X. Putting this back into our expression, we can see what we're going to have is X squared over 0.1 minus X equals 5.6 times 10 to the negative 10. I'm a little smushed. Now, this equation here is going to turn into a quadratic, but we can make our simplifying assumption, because if we go back and say, let's look at this number here, our initial concentration, and let's look at our K. If our K is much smaller than our initial concentration, and my rule of thumb is about 10 to the third power smaller, although the book says 10 to the second power smaller, well, this is 10 to the 9 power smaller, so it is plenty small to ignore. So we're saying that this X is really, really tiny. So we'll say assume that X is much smaller than 0.1, therefore 0.1 minus X is about the same as 0.1. So we go back to our equation and we say we can pretty much just leave out that minus X. So we end up with X squared over 0.1 is equal to 5.6 times 10 to the negative 10. And we can see what's going to happen is if we multiply both sides by 0.1, we get X squared equals 5.6 times 10 to the negative 11. And what we're going to do is take the square root of that number. Now when I do get the square root of that number turns out to be X, which is our hydroxide concentration. And I'm going to take a moment with my calculator off screen and calculate this square root. And I get a number that doesn't make any sense whatsoever. Okay, I went back and got a calculator, and I can find out that X is equal to the square root of X squared, which is equal to the square root of 5.6 times 10 to the minus 11. And when I do that, I get a number that is 7.48 times 10 to the negative 6. And I stop for a second and say, okay, that is the concentration of my hydroxide. Now that I know that, I want to find the negative log of that number, which turns out to be 5.13. And I tell myself, okay, what that really is the POH. And my answer I'm going to get is by taking 14 minus the POH to get my pH. And when you do that, I get an answer of 8.87. And this is a little messy, but you can find that that's the pH of my solution. And that actually makes sense because that's greater than 7. It's a little bit basic, and that's what happens. Sodium acetate. The acetate ion is the conjugate base of the weak acid acetic acid, and when we put it in water, it makes the solution basic. And I have a pH 8.87 times 10. No, 8.87 is the pH.